Hello everyone. In this video we are going to look at vibrations of a continuous system, a string. And we mostly focus on free vibrations here. So here is an infinitesimal element of a string, and there are some assumptions that we have here, and you can see them on the top left. So one is that the tension in the rope or the string is constant. Okay, you can see that here. So on the left side and on the right side it's constant. If you don't know under what conditions this assumption is valid, I have a video under my playlist Statics and Solid Mechanics Machine Design. You can watch it and it tells you when this assumption is valid. The other one is the deflection here, y, is measured from static equilibrium. Rho here, the parameter that we'll use is the mass per length, and the slopes, and specifically the deflections and the slopes, both of them actually, are small. So the angles are very small. So I can say that sine of the angle is approximated by the angle itself. Okay, and we'll see that here. So we look at this element, and again, since it's the deflection is measured from equilibrium, the gravity is not included. We only have tensions on the left and right at two different angles, theta and theta plus derivative of theta with respect to x times dx, which is the increment in theta, right? And so if we write some of the forces along the y direction, so we're going to get this, right? T times sine of the angle. As I said, sine is approximated by the angle itself. T times sine of this angle upward, T times sine of this angle downward equals mass of the element times acceleration of the element. So this is mass of the element, and this is acceleration of the element in the y direction. And mass here is, of course, the length of the element dx multiplied by mass per length rho. Now when you do that, these two t theta terms would cancel. Also, from what's remaining, the dx term will also cancel. So you get what? You get t partial of theta with respect to x equals rho second derivative of y with respect to t. Now remember, theta is the angle itself, is the slope, so it's derivative of y with respect to x. So this term is going to be second derivative of y with respect to x equals that. If you basically divide both sides by t and denote square root of t over rho by c, you can write the governing equations as partial of y with respect to x second derivative equals 1 over c squared second partial derivative of y with respect to time. And this is known as the 1D wave equation, okay? And c here is the speed of wave propagation through the string, okay? And if you see 2D or 3D wave propagations, then you have a function that is, it has basically two variables, like so z is a function of x and y as well as t, and then it will be something like second partial of z with respect to x and second partial of z with respect to y. When added together, this is equal to what? 1 over c squared second partial of z with respect to time. So this is the 2D wave equation, and if there is another one, it's 3D, and you can write this as del squared of z. Okay, so this is 2D, but this is the 1D because our medium is 1D here. And again, you see I did not put any external force or anything on the string. Okay, it's just subjected to own internal forces. So this is free vibration equation. And now the goal is to solve this. Now here, since the only thing we have is product between the terms, nothing else, no addition, subtraction, so we should be able to use separation of variables. So we assume the y, which is a function of x of t, is the product of an individual function of x times an individual functions of t. If I plug these two into 1, you'll get f double prime g equals 1 over c squared f g double dot. And note that here we use double prime for x derivative, and we use double dot for what? For time derivative. If you divide both sides by f times g, then you'll get this equation, that f double prime over f equal g double dot over c squared g of t. Now the thing is, the left hand side is only a function of x, the right hand side is only a function of t. And this equality can never be true unless both of these sides are equal to a constant, because a function of x can never be equal to a function of t unless they are both constants. Now the question is whether this constant is negative, it's positive, or it's zero. And I can show you the only possible solution for it is negative. And here, in order to investigate that, we need to consider some boundary conditions. And the string we consider is what we call fixed. So it's fixed on the two ends, like for example the string on a guitar. Okay, so it's fixed here and fixed here at x of 0 and x of L. And I'll show you that the only possible scenario for this constant is a negative. Otherwise, 0 and positive will not satisfy the boundary conditions. Okay, now why is it that 0 and positive will not work? Well, let me show you. So here, if we assume this constant equals 0, right, then f double prime over f is 0, so it means f double prime is 0. And when f double prime is 0, that means f is a linear function of x. So f is like ax plus b, right? And you need this f function to be 0 at the left side, and it should be 0 at the right side, right? Because our boundary condition are what? Are y at 0 at any time is 0, y at L at any time is 0. That means f at 0 has to be 0 and f at L has to be 0. Now, could that be a possibility here? If you plug in f at 0 equals 0, that means b is 0. And then f at L, once b is gone, it's going to be a times L. If this is 0, L is not 0, so a is 0. And if both a and b are 0, that means f is 0. And if f is 0, that means y is 0. And that's not a solution. Okay, that we might call it trivial solution. Okay, so that's not a possibility. A line with a slope, a non-zero slope, is not a possibility. Now, what if this constant is bigger than 0? So here it's constant, but it's positive. That means that f double prime is equal to some positive number, whatever you want to call it. Let's call it k, not c, to not mistake it for or get confused with that speed of the wave. So that is equal to something like this with this k positive. You know, the solution to this is clearly an exponential function. So it is like a times e to the square root k times t, right? That's what the solution is, or plus b times an x, not t actually, it's a function of x. And then negative square root k times x. And you know, exponential functions just go up or go down, and there is no way that you can pin them down on the two ends. So in this case, again, you'll find out the only solution is going to be both a and b are 0. And again, that's not a possibility. So we have to have it as a negative constant. When it's negative, as you know, the solution is a harmonic function, sine and cosine. And I can show you that. You're going to see it right now. If it's a harmonic function f, then we can set it both to be 0 at the beginning and at the end. So the only solution for this constant is to be negative. Now we assign that negative constant to be what? We call it negative of omega squared over c squared. Why c squared is also used to get rid of that c squared and this c squared. And why omega is used? Because you know that if this f or g are harmonic functions, right, then for a harmonic function, g double dot equals what? Equals negative omega squared times g, where omega is the frequency of that harmonic function g. Okay, you see that? And this omega that we are using here is really the natural frequency of the system. So let's go ahead and go with this proposed solution that both constant and they are equal to a negative, that is a negative omega or omega n squared over c squared. With that, let's see what solution we can get. So the left-hand side of this equality equals that constant, the right-hand side equals to that constant. That means f double prime plus omega over c squared f equals 0, g double dot plus omega squared g equals 0. So g is of course going to be d sine omega t plus e cosine omega t, and f is going to be a sine of omega over cx plus b cosine of omega over cx. Both are harmonic functions. Good. Now, can we satisfy everything? Yes, I'll show you. The first is boundary conditions. Y at location 0, the left end, at any time point is 0. Y at the right end, L, at any time is 0. Well, since it's at any time, then it means the f function at 0 has to be 0. That means b is 0, right? Because when you plug in x of 0 here, this term will go away. This term will become b. So b has to be 0. So your f is simply a sine omega over cx. Now, this function at L has to be 0. That means a sine of omega c over L. Omega over c times L equals 0. Now, a cannot be 0, otherwise f is entirely 0. So the sine term has to be 0. And when sine of something is 0, means that thing, whatever it is, has to be an integer multiple of pi. So it has to be n times pi, where n is a positive or negative integer. In this case, we go with positive because we want the natural frequencies to be positive. If that's the case, from here we can find omega, multiply both sides by c, divide by L, and we get this very important formula, equation 6, which gives us what? The natural frequencies of this system, n pi over c, and remember c was the square root of t over rho, divided by L. Question, how many natural frequencies does the system have? Well, clearly what? Infinitely many. This n can go from 1 to infinity. It's a continuous system, and as you know, in continuous system, we have infinitely many small masses, right? This mass, this element dx, right? How many of that could you squeeze inside this string here? Well, I can squeeze infinitely many. So for each one of them, there is a degree of freedom and there is a natural frequency. So you have infinitely many natural frequencies which follow this formula. And then what is the mode shape associated with each frequency? Well, remember the mode shape is what? This function here, sine of omega over c times x. And here I'm going to replace omega over c here. From this formula, omega over c is what? If you divide both sides by L, it's going to be n pi over L. So I replace that n pi over L up here. It's going to be sine of n pi x over L. So the mode shapes are what? Sine of n pi x over L, when again n goes from 1 to infinity. So the mode shapes are like what? Like the one I showed you in one of my previous videos. I guess it was this one. Look, remember? This was the mode shape, and here this formula I showed you, that was frequency in hertz, not in radians per second. Here I showed you the one for radians per second, and if you remember in this video, this was for n of 1, right? This is when n is 1. So your mode shape becomes sine of pi x over L, which is 0 at x of 0 and x of L. This is for n of 2, so it becomes sine of 2n pi x over L. This function is 0 at 0, L, and L over 2. So you get a node here in the middle, as well as the left and right. And then when n is 3 down here, you get sine of 3 pi x over L. So now the function is 0 at x of 0, x of L, and then 1/3 of L and 2/3 of L. So you get 2 nodes in the middle. And you can see as I go down in the mode shapes, I'll always get what? 1 node extra as I go down. So I have no node in the middle, 1, 2, 3, and it keeps adding 1 node. Okay, so these are the mode shapes, and those were the natural frequencies. So I found 2 very important things. Now the last thing is, can I find the general form of the solution, y of x and t? Remember, this is what we needed to find. Can I find this? Yes. So what is it that we have not found so far in f function? The only thing we could not find is this constant a. And g has two other constants, d and e. So when I multiply f by g to get y, I call this a times d and a times e two new constants. I call them g and h. So my y is going to be h times sine omega nt plus g times cosine omega nt, the whole thing, that's your g, times sine of n pi x over L, that's your f. And why do I have a summation? Because remember, this omega n, you don't have one of that, you have infinitely many of that. Okay, so these terms, these g's and f's that I find, these are g's and f's for any specific n. So this is like gn, and I should not really call it g maybe, because g is that original function. Maybe that notation of calling it g was not really a good notation. Maybe I call it p if you don't mind. So I can, and it has to be, this guy should be, let's see. So d is for the sine function. So this is h and this is p. Let's make sure our notation is correct before we make any mistake. And yes, we don't have any h or anything, so that stays with h. This one I change it to p if you don't mind. And so our solution is what? An infinite series of all of these terms. Okay, so this is your complete solution, 7. And now the question is, this p of n and h of n, they are determined how? Well, from initial conditions. So far we have not talked about initial conditions. Remember, this PDE that we have, this partial differential equation, is second order with respect to time and second order with respect to x. So it needs two boundary conditions and two initial conditions. So far we applied the two boundary conditions up here, but not the two initial conditions. So here, for initial conditions, we assume we release it from rest. So the y dot is 0 at time of 0, and the initial position that you release it, it's some arbitrary function q of x. If that's the case, then y dot at x and at time 0 is going to be this function, right? Because when you take derivative of this guy becomes negative sine, this guy becomes cosine, and at time 0 this guy will go away, cosine becomes 1, so you only get hn. Of course this omega n will also come out, multiplied by sine of n pi x over L, that is 0. The only solution for that is h is 0. And then y at time 0, which is going to be this guy, that's equal to q of x. And if you look here, this is very similar to a Fourier series. So I can find these pn's the same way that I found them in Fourier series. And so here I need to multiply both sides by this sine function and then integrate, right? I need to multiply q of x by this function, integrate from beginning to the end, multiply by 2 over L. So this is how you can find Pn and Hn. And that's all it is to find the complete solution. So now what I want to show you is a simulation that I created in MATLAB. And to simulate this system, I used the finite difference algorithm. And I used the same initial condition and boundary condition, and I chose a function for q of x that I'll show you. So here, for the second derivatives with respect to x and time, I used the 3-point center derivative, right? I used these basically operators for the second derivative, right? Y of the next point and previous point added minus 2 times y of the current point divided by the step size squared. And if you plug it in, you'll get this version, the discretized version of the equation. And the goal here is to find this guy here, the next time point. If you have the current time point and previous time point and the nodes to the left and right and your current node, you want to find the current node at the next time point. So you solve for this. If you do that, you'll get this bottom equation. This is your update equation. This is your recursive update equation. So you see here, if I want to have the value of any node at the next time point, what I need is the value of that node at the current time point, as well as the previous time point, and the points on the left and the right side of it at the current time. And it's multiplied by this constant c squared dt squared over dx squared, where dt squared is the step size and dx squared is the element size or the grid size. So this is the update equation. And how would you apply the boundary and initial conditions? Well, the boundary conditions are easy. Y at x of 0 and y at x of L at any time point is 0. These are your boundary conditions. And for initial conditions, y at x and any time point is q of x. And then y dot at x and 0 is equal to 0. And for y dot, I use the forward finite difference operator at time of t of 0. And if that's the case, when this is 0, it means numerator is 0, which means y at x and dt equals y at x and 0, and y at x and 0 is equal q of x. So y at x and 0 equals y at x and the next time point dt, and they are all equal to what? Q of x. So these are your what? Initial conditions. So I'm going to simulate these two in MATLAB. And the important thing is, can I pick dt and dx any way I want, with any size I want? The answer is no. If you pick them arbitrarily, your update equations might go unstable and you don't converge to actual solution. So there should be a relation between dx and dt, and that is provided here in this formula. C dt over dx, which is the square root of this update parameter, it has to be less than or equal to square root a1 over a2. What is a1? What is a2? They are the sum of absolute weights of the operator, finite difference operator you used for the time derivative, second time derivative, and the one you use for the second x derivative. What does that mean here? Well, let's go back. We can find it here. So it says, look at this operator that you chose for x. Look at the gains that you have in the numerator. You have a 1, you have a 1, you have a negative 2. Take absolute value of these guys, add them together, you get a 4. So a2 equals 4. Then look at the same thing for the t. Again, you see sum of absolute values is 4. So in this case, both numbers are 4. And you could have used other operators for approximating second derivative. In that case, a1 and a2 would be different. So in this case, they are both 4. That means c dt over dx has to be less than 1. So if you pick a specific size for the grid size, from here, you have to pick some dt that satisfies this inequality, the time step. Otherwise, your system can go unstable. And here, let me show you my code. So this is my code. And I picked the length of the string to be 65 centimeters, which is the length of a typical guitar string. And I chose a lot of elements here. Okay, so I chose about 1.2 centimeters for each element. So I'm going to get lots of elements, right? I'm going to get more than 50 elements here to make it a good approximation. And then the final simulation time, I use 5 seconds. And you see, for stability, I had to pick a time of 0.1 millisecond. And here, down here, I checked the parameter c dt over dx, which in my code I call it alpha. This alpha has to be less than 1, otherwise it's unstable. Now, how did I calculate c? Well, the tension I used was 80 Newton, which is again an average tension in a guitar string. The mass density per length, I used 7.2 grams per meter, which is again for a string made of plastic in a guitar. And I calculated C. And if I run this part for you, you can see that The speed of wave propagation is 105 meters per second, and you see my alpha is less than 1.84. So I'm good. And you see that I have how many elements? I have, if you look at X, I have 53 elements. 53 elements and 50,001 time steps to go for just 5 seconds. Then here I started my Y. For my Y, the JJs represent the node location, and II represent the time step. So it's Y of X and T. And you see that I started all of them at 0 with size N and M, where N the number of nodes, M is the number of step times. So I pre-allocated basically Y with all 0, and then I start filling it. So here you see Y at the node 1 and the end node at any time point is 0. These are our boundary conditions. Then Y at any location at time 1, here this is my Q of X function. It's equal to X times L minus X times 0.08. Now how did I pick this one? Well, you can choose any Q function that you want as long as what? There is a condition that you need to satisfy. What condition? Can you pick any Q function? Yes, as long as this Q function here satisfies what? Let me write it for you. So this Q function, it has to satisfy, let me type it for you. Q of X has to satisfy the boundary conditions, i.e. in here Q at 0 should be equal to Q at L should be equal to 0. If that's not the case, then you're gonna have problems. Okay, so whatever function that you choose, make sure that it satisfies, in this case, what? The initial conditions. Okay, so I'll put that for you down here so you know that this Q of X has to satisfy, and in this case you see it does, because it's X times L minus X, so it's 0 at 0 and L. Now where did I get this constant from? So I picked this constant such that when I run this part, the maximum Y that I get at the beginning, if you look at this Y max, the maximum displacement I get at the beginning when I'm plucking the string on the guitar is about 8.5 mils. So if you, when you're picking on the strings and playing guitar, if you move the strings more than 8.5 mils or less than that, then you can change this number. Okay, so this is just to scale it right. And you see Y at the second time point is the same as Y at the first time point for all locations. Where does that come from? This is this condition here, applying the Y dot equals 0. So now I got everything under control, and I run my update equation for all nodes for all time points, and then finally I do an animation for you here. So let's go ahead and run it. Here we go. 53 nodes for 5 seconds. There we go, right? So I'm gonna upload this file for you on under the video playlist. I give you a download link. Feel free to play with it and learn from it. And hopefully this video was useful to you, and you learned how to simulate and how to solve the vibrations of a continuous system like a string 1D wave equation. And I'll see you in my next video. Thank you.